Hello and welcome back. This is the last section of chapter 3. It's about control flow, the ability to run some code depending on whether a condition is true, and the ability to run some code repeatedly while a condition holds true are basic building blocks in most programming languages. The most common constructs that let you control the flow of execution of Rust code are if expressions and loops. If expressions. If an if expression allows you to branch your code depending on conditions. You provide a condition and then state. If this condition is met, run this block of code. If the condition is not met, do not run this block of code. Create a new project called branches in your projects directory to explore the if expression. In the main file, input the following: a variable number with value 3 and default type i32. If the number, so one differentiation when compared to C is that the if statements do not require surrounding brackets, surrounding parentheses. All if expressions start with the keyword if, followed by a condition. In this case, the condition checks whether or not the variable number has a value less than 5. If it has less than 5, then the condition was true. Otherwise, the condition was false. So here, the condition was true will be printed because number is 3 and we check whether it is less than 5, which holds. We place the block of code to execute if the condition is true immediately after the condition inside curly brackets. Blocks of code associated with the conditions in if expressions are sometimes called arms. Just so here, this block of code is called an arm. This another arm. Just like the arms in match expressions that we discussed in the previous section of chapter 2. So in chapter 2, it was a quick discussion, nothing more. There's a following chapter which discusses much in detail. So here the match in chapter 6. So in 1, 2, in 3 chapters. Here we were here. So we didn't actually miss anything by not reading chapter 2. Chapter 1 and chapter 2 are both introductory. Chapter 2 contains a simple program. Literally, it does not even have subsections. It's just a solid one section. And here, getting started, it just walks you through the installation process. Includes an example for printing hello world, and then using the cargo for pulling the dependencies of your project. So let's continue. Optionally, we can also include an else expression, which we chose to do here, to give the program an alternative block of code to execute should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of code. So it's totally ignored. Try running this code. You should see the following output. So we speculated that this here should be printed, which is, it's consistent. Let's try changing the value of number to a value that makes the condition false to see what happens. Any value from 5, including 5, till the maximum value of I32, so the signed integer of 32 bits, which here in data types we had here a small note about its range. Where was it? Here. Each signed variant can store numbers from where n is the number of bits, where n is the number of bits that variant uses. So for I32, substitute n for 32 minus 131, so 32 to the power of 31, calculate that, and then subtract 1. So that's the maximum value that we can assign to the variable number. If we use a larger value, then maybe so something interesting here happens. Then maybe the default type for number will change from I32 to the next bigger, or to an appropriate type which can capture the magnitude of the number we want, but no bigger. If it can fit inside I64, then I64 may be used. A second observation here is that if number is I64 and 5 here is an expression which has a type, which will be I32 because that's the default type for integers, then we will compare an I64 with an I32 type. This comparison is not inherently problematic, but maybe if we instead used a big enough negative, a small enough rather negative value to initialize number to warrant an use I thought that the U types are negative only. So yeah, so the example that I wanted to make, the point I wanted to make, there may be, the idea is, the key takeaway is maybe that there can be cases where the two types compared here could be a bit, you know, difficult. In C, if you've programmed in C, you know this. When you compare a signed number with an unsigned, I think a warning is issued by the compiler. So there's that. Okay, so here's, we read this and okay. Here, if we set the value of number to 7, this means that is 7 smaller than 5? No, 7 is bigger than 5. So this is not, the condition does not hold. So the condition was false. The else arm will be executed. Here, as we can see, it's consistent with what we speculated. It's also worth noting that the condition in this code must be a bool. If the condition isn't a bool, we'll get an error. For example, try running the following code. The number is 3. If 3, then number was 3. The if condition evaluates to a number, to a value of 3 this time, and Rust throws an error. Expected bool found integer. Mismatch types. The error indicates that Rust expected a bool, but got an integer. Unlike languages such as Ruby and JavaScript, Rust will not automatically try to convert non-Boolean types to a Boolean. You must be explicit and always provide if with the Boolean as its condition. So eventually, at the, let's say, the root level of the expression, as the condition for if, the final type of the expression should be a Boolean. It can be composed of other types. For example, here we could ask, is 3 equal to 3? The same, using double equals. The comparison is such comparison like we used here, result in a Boolean. Okay. Okay, well, we read through this. Okay, you must be explicit and always provide if with a Boolean as its condition. If we want the if code block to run only when a number is not equal to 0, for example, we can change, for example, we can change the if expression to the following. The number is 3. Please run the arm of the if only when the number is different than 0. Here the number is 3. 3 differs from 0. Yes. 3 and 0 are not equal, so this here runs. Running the code will print number was something other than 0. Handling multiple conditions with else if. You can use multiple conditions by combining if and else in an else if expression. For example, here in the function main we declare a variable number with value 6. If the remainder of the division 6 and 4, 6 over 4 is 0, which is not, it's 2, then this here will be printed. The number is divisible by 4. Here, this is the arm that will run. The number is divisible by 3. It's also divisible by 2, but this arm will not run. Only one arm of an if, else if, and so on and so forth, and with the optional else at the end, only one arm of such expression runs. This program has 4 possible paths it can take. After running it, you should see the following output. Here, the number is divisible by 3. So this line is run, and this line here is not being executed. When this program executes, it checks each if expression in turn and executes the first body for which the condition evaluates to true. Note that even though 6 is divisible by 2, we do not see the output numbers divisible by 2. Nor do we see the number is not divisible by 4, 3, or 2. Text from the else block. That's because Rust only executes the block for the first true condition, the arm, synonymously. And once it finds one, it doesn't even check the rest. Using too many else-if expressions can clutter your code. So, if you have more than one, you might want to refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases. Yeah, we saw that previously. Using if in a let statement. Because if is an expression, we can use it on the right side of an let statement to assign the outcome to a variable, as in listing 3.2 here. Here we have a variable named condition, which is being initialized with the value true. So this is a boolean. It's also immutable. We also set a variable number with the resulting value of this expression I've highlighted. This expression evaluates to 5 when the condition holds and to 6 when it does not. So condition is true, so this here is true, so 5, so the number is being initialized by 5. If it was false here, then it would be initialized by 6. If we didn't have an else arm, then I speculate that Rust would throw an error, because here, if this if the condition holds, then the type of number would be i32. If it does not hold, then its type would be the unit type, because it will implicitly return the the unit value. So it could have two values, two different types. If we add a random value as to initialize the variable condition, would be this would be convincing that we do require an else arm and both of these arms to generate the same type. Otherwise, we would have a problem. This is what they speculate here. The number variable will be bound. So here, the number will be bound to a value based on the outcome of the if expression. This is the if expression. Run this code to see what happens. Here, the output is 5, which is consistent with what we speculated. Remember that blocks of code evaluate to the last expression in them, and numbers by themselves are also expressions. In this case, quick question. What would happen if I add an expression here 3.5 I have a function in main which calls the function foo and then ends. And here the function foo does 5 and then let x equals 8 or whatever. Here, this is the final expression, the 5. There is a second expression, which is the 8 here, but maybe Rust parses it to be of this statement, let x. Let's see, does this run? Let's try to compile. No, unexpected closing delimiter in the line 3. This is 3 here. Why does it? Oh, yeah. Add semicolon. Unexpected token. Here the let is an unexpected token. So what if we what will happen if I do this? Will this here be an expression in itself, which consists of a single instruction, 5, and the 5 is itself an expression. So this here is, does this work? Yeah, it's unnecessary, but yeah, so mismatch types, expected, the unit, but found integer. Yeah, so Rust, the foo function here, we said that it does not return. Can we say that it returns void? Is that not found the scope? So void actually is the unit type. So unitype and void is the same thing when existing in the universe of C and Rust. Okay, so okay, there's that. I32. Let's run this here, and let's here print line macro, and here have this inside and substitute it formatting foo returned this. Okay, so let's compile. Let's run 3. Oh, nothing's printed. Why? Oh, there's an error. Which here's the error. Expected because of this opening brace. Yeah, is there a problem? No, I don't want to escape it. I just want to print this here. This is an expression. How can I do this? Maybe, if I remember correctly, the other way is to include an empty and then call compile and here. Yeah, so it's 5, and also we can add infinite number of matching of valid here and curly braces. So imagine 3 warnings omitted. Yeah, here it unwraps. Remove this and has a single, and then it wow, it's like an onion now. There are the outer curly brackets are being peeled, and Rust here says that this would be better, but then it goes ahead and peels the inside too, and say if you can choose one or the other. Here the red braces are the outer ones, whereas here the innermost are being highlighted. Oh, that's cool. What if we add 3? So here for the outermost, and then for the next deeper level, and then for the innermost. Yeah, so it's okay. I wanted to check if all the combinations had been enumerated by the compiler, but no. That would be cool if it did happen. Probably it would also lead to a problem where the enumeration in itself is infinite for some reason. What maybe we could write an expression that takes um, uh, the fact that it's been enumerated by the compiler and make the compiler not terminate. So I guess it's uh, um, it's it would be a mistake to enumerate all the um, removals of the matching curly brackets. Okay, um, so yeah, where were we? Here, remember, here, in this case, the value of the whole if expression depends on which block of code executes. This means the values that have the potential to be results from each arm of the if must be the same type. In listing 3.2, the results of both the if arm, where's the 3.2 here, and the else arm were i32 integers. If the types mismatched, as in the following example, we'll get an error. Oh, I unintentionally we went through this. I talked about if the else arm wasn't there, what would happen. Here, instead, the else arm explicitly exists, and not implicitly. If it didn't exist, it's like it exists implicitly, and it returns the unit. It returns void, because the unit value and void are synonymous. That's the I try to map my knowledge of Rust as I accumulate it to my existing knowledge about C, because C is also a systems language. Okay, so if it's explicitly written and 6 here is a string, we'll get an error. When we try to compile this code, we'll get an error. If and else arms have value types that are incompatible, and Rust incompatible, not different, but incompatible. Maybe they could be different, but compatible. I don't know what it means to be different but compatible, but there's that. Rust indicates exactly where to find the problem in the program. If and else have incompatible types. Here, the 5 expected because of this expected integer and found a reference string. I don't know what's this with the reference of with the ampersand character. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work, because variables must have a single type, and Rust needs to know definitely at compile time what type the number variable is. Knowing the type of number lets the compiler verify the type is valid everywhere we use number. Rust wouldn't be able to do that if the type of number was only determined at runtime. The compiler would be more complex and would make fewer guarantees about the code if it had to keep track of multiple hypothetical types for any variable. Repetition with loops. It's often useful to execute a block of code more than once. For this task, Rust provides several loops which will run through the code inside the loop body to the end and then start immediately back at the beginning. To experiment with loops, let's make a new project called Loops. Rust has three kinds of loops: loop, while, and for. So it has one more than C. It has also a loop. Let's try each one. Repeating code with loop. The loop keyword tells us to execute a block of code over and over again, either forever or until you explicitly tell it to stop. As an example, change the main file in your loops directory to look like this. Here, the function main has only a loop. Here, a loop, and then its body follows. Okay, so question: can if inside can I have here's the loop. What if I don't have? Will this work because it has one instruction inside? Yeah, I meant to do this. It only lists. Oh no. It cannot do this. It needs it's an error. It needs it has one error here. Did one previous error. Yeah, the warnings, we know about them. So if it has one instruction, then we can't omit the curly brackets. They must be always emitted. Okay. So now it compiles. All right. So it does not work for loop, but maybe it works for other control flow expressions. Okay. When we run this program, we'll see again printed over and over continuously until we stop the program manually. Most terminals support the keyboard shortcut Control C to interrupt the program that is stuck in a continual loop. Give it a try. Okay. Yeah, so in Linux, that's it's a known feature of the terminals. Control C sends the terminal rather sends to the program the SIGINT interrupt. You may or may not see the word again printed after the hat C, depending on where the code was in the loop when it received the interrupt signal. Fortunately, Rust also provides a way to break out of a loop using code. You can place the break keyword within the loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in the chapter 2 to exit the program when the user won the game by guessing the correct number. We also use continue in the guessing game, which in loop tells the program to skip over any remaining code in this iteration, in the current iteration of the loop, and go to the next one. Returning values from loops. One of the uses of a loop is to retry an operation you know might fail, such as checking whether a thread has completed this job. You might also need to pass the result of that operation out of the loop to the rest of your code. To do this, you can add the value you want returned after the break expression you use to stop the loop. Okay, so that's cool. It's like return. It's like writing a return, but inside the loop. You just do break instead. Break 5. Yeah, no, yeah. Here it is. That's cool. Um, the value will be returned out of the loop so that you can use it. So here's the loop. Here's the expression, the loop expression, which returns the value that is the result, this expression here. So to return this expression that I've highlighted, we must first evaluate it. So when the counter is 10, we double it. So it becomes 20. So result is 20. So we keep increasing the counter, which starts from 0 and is correctly set as mutable variable. The loop runs 10 times, turns for 0, 1, 2, and in the end, in the 11th iteration, 0 through 9 is 10 iterations. It then attempts to run the 11th time, but it does not complete because it stops here at the break since the condition is true. Counter will be 10. Okay. And we print 20 because it is doubled. Before the loop, we declare a variable named counter and initialize it to 0. Then we declare a variable named result to hold the value returned from the loop. On every iteration of the loop, we add 1 to the counter variable and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter times 2. After the loop, we use a semicolon to end the statement that assigns the value to a result. Here. This is the statement, and statements need semicolon at the end of them. Finally, we print the value in a result, which in this case is 20. You can also return from inside the loop. While break return from inside the loop, while break only exits the current loop, return always exits the current function. Yeah. Okay. Yeah, this here is consistent with C as well. We can return from any point anywhere we are. In any scope. So, okay, let's continue disambiguating with loop labels. If you have loops within loops, break and continue apply to the innermost loop at that point. You can optionally specify a loop label on a loop that you can then use with break or continue to specify that those keywords apply to the labeled loop instead of the innermost loop. Okay, so that's cool. It's a cool semantic feature, but I can see that this could lead to some unreadable code if abused. Loop labels must begin with a single quote. So where is it? Oh, here. So this is how we assign a label to the outermost loop, which starts here and ends here. Isn't that right? Yeah. I think everything aligns. Yes. Um, Loop labels must begin with a single quote. Here's an example with two nested loops. Here the outermost loop is called counting up. That's its label, followed by the colon. The outer loop has the label counting up, and it will count up to 0 starting from up to 2 starting from 0. The inner loop without label, this one, counts down from 10 to 9. The first break that doesn't specify a label will exit the inner loop only. Here, there are two break statements. This one is without a label. The break counting up statement will exit the outer loop. This code prints this is what it prints. We could go through it, but it's a very spaghetti code. And we and even if we did, we would not gain any insight or additional knowledge. If you want for exercise, you can do it. Streamlining conditional loops with while. A program will often need to evaluate a condition within a loop. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break, stopping the loop. It's possible to implement behavior like this using a combination of loop, else, of loop, if, else, and break. You could try that now in a program, if you like. However, this pattern is so common that Rust has built-in language construct for it, called a while loop. Listing 3.3, we use while to loop the program 3 times, counting down its time, and then after the loop to print a message and exit. So this is a simpler program. So we start from 3. As long as we are not, as long as we are different than 0, we print. So it's 3 and then 2 and then 1 and then we become 0, but 0 is not different than 0, and then so 3 to 1 liftoff should be the output. This construct eliminates a lot of nesting that would be necessary if you used loop, if, else, and break, and it's clearer. While a condition evaluates to true, the code runs. Otherwise, it exits the loop. Okay, so previously I noted about if we abused the break and in combination with the labels. I think that it is possible to do this behavior in C as well, but without using break and labels. Instead, we would use flags. Set the flag break and then check again, and if the flag was set, break again to to um, you know terminate the innermost loop and continue in the next surrounding loop that we are in. If we had two or more loops nested, yeah. So maybe it's not inherently a Rust's problem. It's instead, actually, it improves the readability of such cases, which it's helpful. However, I think that in any case, such implementation should be avoided. Don't nest multiple loops and use flags to terminate that's not readable. It's not easy to follow. Okay, yeah. Here, continue here. This concept eliminates, yes, looping through a collection with 4. Okay, we are nearly done. You can choose to use the while construct to loop over the elements of a collection, such as an array. For example, the loop in listing 3-4 prints its element in the array A. Here is the function main, and we have an immutable array A stored in the stack of type I32 semicolon 5. The, the type is this the 5 items of I32 each, and it's not mutable. And then we have an index. While index is less than 5, we print the value that lives inside A at slot index, and then increase the index. So we will print the contents of the array. Here the code counts up through the elements in the array. It starts at index 0 and then loops until it reaches the final index in the array. That is, when index is less than 5 is no longer true. Running this code will print every element in the array. So 10, 20, 30, 40, and 50. All 5 values appear in the terminal. As expected, even though index will reach a value of 5 at some point, the loop stops executing before trying to fetch a sixth value from the array. However, this approach is error prone. We could cause the program to panic if the index value or test condition is incorrect. For example, if you change the definition of A to have 4 elements but forgot to update the condition to while in index less than 4, the code would panic. It's also slow because the compiler adds runtime code to perform the conditional check of whether the index is within the bounds of the array on every iteration through the loop. So here when we access the array's element at the specified index here, such check runtime check is being performed. Whereas if we look at how this for is structured, there is no such syntax present. So for element in A, this probably inside maps to a similar intermittent representation to the one generated by this while statement, or while expression rather. These are expressions now because they return a value. Yeah, but it lacks the runtime check. Okay. As a more concise alternative, you can use a for loop and execute some code for each item in a collection. A for loop looks like the code in listing 3.5. When we run this code, we'll see the same output as in listing 3.4. But importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. Yeah, we just need to check if when we change array A, we don't have to change the boundary index and the current the boundary index as we would have here we should have changed 5 to the new bigger or smaller boundary index. Machine code generated from for loops can be more efficient as well because the index doesn't need to be compared to the length of the array at every iteration. Using the for loop, you wouldn't need to remember that to change any other code if you changed the number of values in the array, as you would with the method listed used in listing 3.4. So this is 3.5, 3.4, the previous one here. We went through this just now. The safety and consciousness of for loops make them the most commonly used loop construct in Rust. Even situations in which you want to run some code a certain number of times, as in the countdown example that used a while loop in listing 3-3, this one here, 3-2-1 liftoff, most rustaceans would use a for loop. The way to do that would be to use a range provided by the standard library, which generates all numbers in a sequence starting from one number and ending before another number. Here, here's the countdown. Here's how the count. Uh, Here's what the countdown would look like using a for loop and another method we've not yet talked about, rev, to reverse the range. So here's how it looks for number in range 1 through, but not including 4, 1, 2, 3, but reversed, 3, 2, 1, liftoff. It is a bit nicer, yes, but the syntax here is rather niche. It would be better if there existed like in Python, the range. I think it's a function which returns a list with the numbers. In Python returns a list here. It isn't required to return a list, so that the performance isn't being decreased. The summary of the chapter, you've made it, of the whole chapter 3, that is, you made it. This was a sizable chapter. You learned about variables, scalar and compound data types, functions, comments, if expressions, and loops. To practice with the concepts discussed in this chapter, try building programs to do the following. Okay, so if expressions and loops, compared to C, if expressions and loops are not expressions, meaning they do not return a value. They variables are mutable by default in C. Here they are not. C also has scalar data types, but it lacks compound ones. A function cannot return two values using a tuple. Tuples don't exist. And there isn't an explicit differentiation between expressions and statements. There might be, but it's not as apparent it is in Rust. The programs we could implement as exercise are convert temperatures between Fahrenheit and Celsius. We will implement those in the next video. Generate the nth Fibonacci number. I will provide two solutions. One using the bottom-up solution, starting from the 1, adding 2, and getting 3, then 3, 2 are the next two, and then a loop and generate the Fibonacci numbers up until the nth. You will see the solutions. So this will be a good exercise. I will also implement a recursive solution which will use memoization to um, avoid recalculating sub Fibonacci numbers. I will also include the closed. There is a formula for computing the nth Fibonacci number. I will also include the solution. There's a closed formula. In this solution, we will compute the nth Fibonacci number in O1 in respect to the input, the n. And then the third is print the lyrics to the Christmas Carol, taking advantage of the repetition of the song. Okay, so maybe this I will skip because it is not as algorithmic as it's not as algorithmic as the Fibonacci number. Okay, when you're ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other programming languages. It's called ownership.